Next, we're going to look at a mathematical example of how to do these calculations and how to figure out what the potential is at any given point for a source charge. And remember, it's only dependent on the source charge, so it doesn't matter what our test charge is as we're doing this. But we're going to look at 2 points away from a charge. Happens to be in this diagram points A and F. But you can see that if we represent this as more of a topographical map, as an elevation, that our positive test charge will tend to want to roll downhill to an area where it is at a lower potential and at a lower potential energy. So here's our problem statement. We have a source charge of 1 nanocoulomb. Nano is again 10 to the negative 9th. Is placed somewhere in space far from other charges, which means we don't have any other charges to worry about. We're just going to worry about this one. We're far enough from the other charges that they are not influencing our potential and electric fields. And we're going to look at a distance of 1 meter and 2 meters away from our charge. And again, this is our equation for potential. And again, KE is 8.99 times 10 to the 9th. Newton meter squared per coulomb squared. And oftentimes I'm lazy and just use 9E9 in the calculator because that's close enough to that value for most applications. Okay, so we want to figure out what the potential is of a half a nanocoulomb point test charge. That's not going to come into our calculation because it's not in the calculation for voltage. When we do our energy, we'll need to know what the test charge is because that value is in that part of the calculation. But for now, we just need to know the source charge, which is the 1 nanocoulomb. So the voltage at point A is our Coulomb's constant times our source charge divided by our distance at A. So that's 8.99 times 10 to the 9th Newton meter squared per coulomb squared. And then our source charge is 1 nanocoulomb, so that's 10 to the negative 9th coulombs. And our distance is 1.0 meters, gives us 8.99 Newton meters per coulomb, which is, we're just going to call that 9 volts. And if I do the same thing then for the 2 meter distance, that has the number to 4.5. So that means our change in distance is, if this one is at 9 volts and this one is at 4.5 volts, then the change is, our delta V is negative 4.5 volts because I went down 4.5 volts. So now we'll look at our diagram. These are the two numbers that we calculated, the 9 volts and the 4.5 volts. Now what we want to do is calculate the change in energy. And here we have a couple of options and we're going to do it both ways. I'm going to do it the easy way first. Using this formula is delta U is equal to Q times delta V, because remember in our boxes we had V over here is KEQ, write the other Q over R, and to go this way I just need to multiply by my test charge in order to get the energy. So that's kind of how I remember this equation. Okay, so we put the values in. So our change in energy is our test charge, so that's half a nanocoulomb, times our change in voltage is negative 4.5 volts, gives us a value of negative 2.25 nanojoules. We can also do that same calculation using the full energy equation, and we get 4.49 times 10 to the negative 9th joules and 2.25 times 10 to the negative 9th joules, and we get the very same answer. Go figure. So I recommend using this equation. If you know the change in voltage, just multiply by the test charge to get the change in energy. Much simpler, but the other way works as well. Now it's your turn to give it a try, so pause the video here and see if you can get this answer. We're going to be looking at the difference in electric potential and the difference in electric potential energy between point A and B here, where point A, we're going to call that 5 volts. It's pretty much close to the 5 volts, and this one's a little hard to tell. So we're going to call that 15 volts. It might be slightly in between, but we're going to call it 15 volts. So go ahead and give it a try and see if you can get the right answers, and come back to the video after you've tried it, and we'll work it together. Okay, hopefully you've had a chance to figure this out on your own, but we want to look at the change in potential. I've already calculated the potential differences, so shouldn't be that hard to figure this one out, but we're going to do V final minus V initial. V final is the 15 volts minus the 5 volts is equal to 10 volts. So if this were to happen without energy input, it could happen with a negative charge, or if it's a positive charge, we would need to add energy. And how much energy is that? Well, we're going to use the more simplified formula. The change in energy is equal to Q delta V. And again, we have a half a nanocoulomb test charge. So we have plus 10 volts times the 0.5 times 10 to the negative 9th coulombs. Or since I'm going to want to give my answer in nanojoules anyway, I could just use the 0.5 nanojoules, and we get an answer of plus 5 nanojoules of energy is required to make that move. Those are the answers nicely written out.